you.
Got that on video.
Right on cue, yeah.
Right on cue, right, yeah.
Yeah, chapter 13 is functions of several variables. Functions of several variables. That's the title of the chapter. I guess we haven't exactly talked like this, although we've been dealing with some functions. But see, we might talk like this now. F of x, y equals some expression involving x's and y's. And I think I'm going to make this one up here. So, I think I just made up a function of several variables. You know, this is the way we talk. We say, you know, this is a function of two variables, but of course a function of two variables equals the third one. I mean, what's another name for this? Z. Good, good. The analogy is, back in two dimensions, we would talk about f of x. We would talk about f of x in two dimensions, but f of x always equaled
Y.
the second variable, y. So it was a function of one variable, but itself equaled the second variable, y. So this is a function of two variables. I mean, the language is almost misleading. It's a function of two variables, but the function itself equals the third variable. So this is a three-variable, 3D situation we're in, a three-dimensional situation, and it's just a surface in 3D is all it is. It's a surface in 3 dimensions that we've been studying. But we might, you know, instead of just some special surfaces, we might kind of just run into a lot of generic functions, generic surfaces, and we might need some skills to kind of look at it and decide what it is. And so one of the skills is to think about the domain of these functions, and maybe even to do this thing called sketch the domain. And so right off the bat, 3 weeks from now, we're going to take a test, and probably the first question on your test is this, right? Sketch the domain of a function. This is, I'm in 13.1, this is of course where I'm starting. And so I'm not asking you to sketch this three-dimensional function. I'm asking you to sketch the domain of this function. I guess maybe I should have started by saying the domain of this function is, it's a function whose domain is, the domain is a region in the xy plane. I mean, I guess we should have known that. The input for this function is a set of ordered pairs that live in the so the, you know, the domain or the input for this function is, I'm going to say it like this, it's a set of ordered pairs. It's a set of ordered pairs that, of course, live in the xy plane, you know, x's and y's. So for this particular one, and then you plug in these inputs, you plug in these x's and y's, and it spits out z's. And z's are your output. And if you wanted to talk about the range, you would be talking about the z values. The book asks you a little bit about range. Range is not my favorite question. I like these domain questions. Range is always a little trickier. Yeah, so the domain is a set of ordered pairs, x, y. They form a region in the xy plane. Can you say anything about the domain of this function? What might you think about what's legal, what's illegal, what's legal input, what's illegal input?
It can't be bigger than 1, the subtraction can't be bigger than 1.
Okay, or what you know is that we work in the real number system, and in the real number system I can't have the square root of a negative number, so you're saying that that thing inside the square root better be greater than or equal to 0. Basically, the thing inside the square root better be positive or equal to 0. But now what does that lead to? That leads to what I think you were saying. You kind of said if you move the x squared and y squared over, you kind of get this statement. Is that okay with you guys? Move the x squared and y squared over, and I got x squared plus y squared is less than or equal to 1. And, you know, messing around with inequalities is not maybe our greatest skill that we have, but we'll get good at it. We need to, but this is a region in the xy plane. If you ignored the inequality and just sketched the x squared plus y squared equal to 1, what would that be?
Circle.
Good, a circle of radius 1 in the xy plane. The x squared plus y squared equal to 1 is a circle of radius 1 in the xy plane. But being less than or equal to 1, what do you think? It's probably the inside stuff. Could be the inside stuff. Could be the outside stuff.
Yeah.
Usually it's pretty logical. I think the x's and the y's squared that are less than 1 are probably the ones
Inside.
interior.
Yeah.
But if you ever get to where you don't feel like you can trust that, you can always do this thing with inequalities. You can pick a test point. So like if you pick the test point 0, 0 and plugged it into the inequality, 0 plus 0 is 0. Is that less than or equal to 1?
Oh, yeah.
Okay, so that's true. And if you get a true statement with your test point, then means shade the side that has that test point.
Mm-hmm.
So this came out true. This interior of this circle is all shaded. It would have worked. It would have been true for any interior point. I just used that 0, 0 as a test point. But here's a good picture of the domain. This is a good picture of the domain. And so whatever this, you know, the z-axis is coming out at you, and there is a three-dimensional surface here. This is a three-dimensional surface, and it lives up above the xy plane, but I tell you what, it only lives over this shadow. This is like the shadow of it. When you're looking at the domain, I mean, it doesn't live over here. You pick some ordered pair over here, there is no function. It only lives right here. So I sort of asked you to analyze this domain right off the bat without really, and you're supposed to be able to analyze these domains without really knowing what the function is, maybe, or what this picture is, but maybe you kind of know. Do you know what this picture is?
It should be an ellipse, right? And then square and then...
Those are good guesses. What if we replace this with a z
Z squared equals.
and squared both sides? Good. If I replace that with and squared both sides, I would get z squared equals this. And then if I moved everybody over, x squared plus y squared plus z squared equals 1. What is that? A sphere of radius 1. And if you're a sphere of radius 1, the shadow you cast onto the xy plane is this, I guess, this circle of radius 1.
But it's also, you cast the same shadow on the XZ and the YZ plane as well.
That's true. I guess we're writing this as z equals a function of x's and y's. That's why I mean, you can change the names of the variables. You could write y as a function of x's and z's and look at sort of a different looking domain but it would be the same domain in this case. In this case. So that's what we ask you to do. I mean, if I said find the domain or describe the domain, that's kind of this statement. But I want more than that. I want a sketching the domain, which means you sketch this statement, which is a shaded region in the xy plane. When I use the word region, that's a shaded region in the xy plane. That's what the domain should be. Hey, you know, at the end of this problem, we discovered or realized or figured out that what we were dealing with was a sphere of radius 1, centered at the origin. You know, we figured that out, I guess. But it wasn't, you know, if we did solve this for z, what happens when you solve for z? You kind of go backwards. You move the x squared and y squared over. You take the square root of both sides. But if you really take the square root of both sides, you should get plus and minus. See, so the plus and minus square root is actually the entire sphere. And I didn't have the plus and minus square root. I just had the plus square root, which is actually just the top half of the sphere. So technically, this is the top half of a sphere, or a hemisphere is what technically this is. And again, that's what he is. He's technically a hemisphere. The radius one. Because of that plus and minus. I mean, we chose the plus square root. Again, to be a function, we got to almost go all the way back to your college algebra days to remember, what's a function. Every input has one output. So we don't want two z values as outputs. We to be a function, we want one output. So I don't want a plus and minus symbol on this. That wouldn't be a function. I want one z output. Here, let's sketch another domain for fun. That's good though. That's good stuff. Here, let's try this guy. All right. Yep. We go from 10 miles per hour to 80 miles per hour in one jump. No, I didn't step it up a notch here is what I'm trying to say. Just a little. If you think about the denominator, let's ignore the numerator for a second. If you think about the denominator, I want you to sketch the domain again. What would you got some thoughts you want to say about?
Circle, radius 2.
Can't be 0.
Good. It's almost the same thoughts as last time, except you've nailed it. You said that this 4x squared, the thing in the square root, better be positive. But also, since it's sitting in the denominator, it ain't allowed to equal 0. It is not allowed to equal 0, so that's a little different than the last problem I had, where it was okay to equal 0. This was in the numerator. This better not equal 0. So when I go to sketch this, well, one more time, if you move the x squared and y squared over, you get x squared plus y squared is less than 4. You're right, this is a circle of radius 2, but watch what I do, you guys. I'm going to write, when I draw the circle, I'm going to use a dashed line as the border. Do you know why it's a dashed line? Because it's not allowed to equal. Yeah. So in my last problem, it was kind of subtle, but I had a nice solid line, and that was because it was allowed to equal that border. So we cannot equal, we're not allowed to equal the 4. That leaves the border as a dashed line. Again, though, would you just guess that the interior is what I should shade?
No.
Yes, the interior is what I should shade. So far, I'm thinking this is my domain with not including the border, but I have totally ignored what's going on in that numerator. So not only do I have to meet this requirement, I also have to meet this other requirement. And what? What do you know about natural log there, or the input to natural log? You got any? It can't be negative. It's kind of like a square root in that sense. The input for a natural log better be positive and not equal to 0. So you're saying, just based on that knowledge about a natural log function, that the product xy better be greater than 0. All right, that's the right thinking. Now, can we sketch that? I mean, what is that saying? I know you have it.
The first and third quadrant.
Yeah, he said the answer. What did he say? He said that if this product is positive, that means, how do you get a product that's positive? Well, the two numbers should be positive. Or they're both negative. But they're not different in sign. That would make them negative. So you're saying to be both positive, that would be numbers in quadrant 1. Or, if they're both negative, those would be ordered pairs in quadrant 3. Yeah, that's what putting this into words would be ordered pairs in quadrant 1 and quadrant 3. By the way, though, again, we don't want it to equal 0. So, you know what I'm not including? What am I not including?
Axis.
The borders, right? The axes. I can't let x be 0. Right? So it is this corner, but it is not including this axis. And it is not including this axis. And I need to make that clear for my teacher to see that. Those little dashed lines indicate I'm not that, I'm not that, I'm not this. Do you know what the final answer is? You've got to meet this requirement and this requirement. I mean, the word "and" means kind of, in mathematics, you could use the word intersection for that word "and." It's the intersection of these two shaded areas. So, yes, so the ultimate domain is what? Is this. Yes, thank you. It's this. It's this. First I had all 4 quadrants, but with this added requirement here, that restricted me to just 1 and 3. So this is not even part of the domain now. It's just quadrants 1 and 3. Bordered, shaded borders everywhere. That's a pretty good question, ain't it? Mm-hmm. I mean, whatever. And again, what's the point of this? It's fun. Don't forget that. But the point is that by sketching the domain, I might have, it gives me a little clue of what this 3D thing looks like. I mean, this is a 3D monster of some sort. It's a 3-dimensional, but I know, but now after analyzing his domain, I know that he lives kind of above these regions. I mean, he doesn't live over here. There is no function up here, and there's no function out here. It's only here. It's only here. Is where it lives, and it might live above the XY plane. Listen, if those Z values are negative, it could live below the XY plane. I often say it's above the XY plane, and it could be above or below. Remember this last one, what was this? This was a hemisphere. It was definitely, and it was the top half of it was above. This one, you might be able to get some negative values or some positive values, so it might live above or below this shaded region in the XY plane. This is a picture of his domain. That was a good one. All right, let's do something else maybe.
Why can't it touch the X or Y axis again?
Yeah, why
I
not?
missed that.
That's okay. It was subtle. This has strictly greater than, and it cannot be equal to.
Cannot be 0. Okay.
And therefore, I can't let the x or the y be 0, or it would equal 0. So I have to, x and y cannot be 0. And that means the x and y axes can't be included.
Okay.
Right. To make this, to keep this restricted, what we looked at when we said this, we said, oh, quadrant 1 and 3, and that's cool. But the little detail is also, x cannot be 0 and y cannot be 0. That's kind of attached to that. Yeah. Any other good questions? All right, here's another thing we do in chapter 13. In 13.1. In 13.1, Here's the other thing we do. We do this exercise called sketch the level curves. What are you guys doing?
Check it out the graph.
Well, thank you. Sketch the level curves of a function. I'm going to say this. Level curves, there's another name for level curves is this, contour lines. Here, let's do it. Here's how it's usually presented like this. Somebody gives me a function. I'm going to do this. I'm going to do something real easy here. Look at this. Somebody gives me a function, and then they say, sketch the level curves or contour lines, and they do it for these certain c values, for c equals 0, 1, 2, 3, 4. That's good enough. I can do it for a lot of c values. Sketch the level curves or the contour lines for this function. Listen, this exercise is another way, you know, this thing called sketching the domain, it was sort of a way of two-dimensionalizing your 3D function. Is that okay with you? I mean, it was looking at the domain, but it was two-dimensionalizing your 3D function, or taking a two-dimensional look at your 3D function. Well, that's also what this kind of is. Listen, these c values they give you are z values. These c values are z values. They are. And by the way, this is z over here. Z equals x squared plus y squared. You guys, you might know what this shape looks like, but I'm just gonna analyze these curves or contour lines. Here I go. When c equals 0, I plug it in for z, and I get this. 0 equals x squared plus y squared. You know, by plugging a number in for z, I've just two-dimensionalized this. Do you agree? Mm-hmm. I've just gotten rid of the third dimension z by plugging in a number for z. I've got a two-dimensional, and I want to sketch that. I want to sketch him. Okay. What is x squared plus y squared equals 0?
Point.
Good. We've joked about this before, perhaps, that it's like a circle of radius 0, which is not a circle, it's a point, right? So there's not much of a curve to sketch. It's kind of funny. It's just a point there at c equals 0. I'm sketching a two-dimensional look here. Let's move to something better. When c is 1. When c is 1, you plug in a 1 for z. Those c values really are just z values. You plug in a 1 for z and you get this. And of course, that's a circle of radius 1. So now I'm going to label it c equals 1, kind of on that curve. That's a contour line, or we call it a level curve of this three-dimensional surface. This is a three-dimensional surface. This is just another name for z. And I guess I'm just sort of looking at his contour line when z equals 1. You know, when z equals 1, you're not in the xy plane. When z equals 1, you're up 1 unit above the xy plane. But what would you be when z equals 1? You would be a circle of radius 1. You would be 1 unit above the xy plane, but when we sketch this level curve, we sketch it as if it was in the xy plane. But we label it with this little thing that tells me kind of where he is. This little label c equals 1 tells me where he is. Here, let's move on. When c equals 2. When c equals 2. It's real easy.
Radius squared.
Plug in a 2 for z, and you get this, and what is this?
Square root of 2.
Circle with a radius, square root of 2. Right. Which is, that's 2, there's 1.4. Here it is. Circle, radius, square root of 2. That's the contour line, c equals 2, or the level curve. It's called, we're sketching level curves or contour lines for each of these c values. What about for 3? For 3, x squared plus y squared equals 3. What's that?
X squared plus square root.
Circle radius square root of 3, which is about 1.7.
Oh boy.
Oh,
And it's actually at z equals 3.
Yeah, and it's actually up at z equals 3. But maybe I got this sort of top-down look at this. And I'm looking at all these level curves. They're all just squashed. They're all just laying in the xy plane. Let's do one more. When z is 4, or c is 4, or z is 4,
circle radius 2.
circle of radius 2. Hey, what if I did 5, 6, 7, 8? When I finally got to 9, what would I have when I got to 9? Circle radius 3? Circle radius 3. Hang on. So that's c equals 9. So in between, this was c equals 4. So in between 4 and 9, there's a bunch. There's 5, 6, 7, and 8. 5, 6, 7, and 8, all in between there, right? See, it's hard to tell on this picture. But this is a picture of the contour lines of a three-dimensional surface. Here's your three-dimensional surface. This is a very basic one that we study. Do you know what he is and what he looks like? No, not quite a cone. Close. A cone's cousin. Yes. A cone's cousin is a paraboloid. Remember those conehead people? Those coneheads?
Yeah.
Yeah. They actually looks more like paraboloid heads. But this is a paraboloid, is what this is. A very circular paraboloid, as we just discovered. It's a very circular paraboloid, and what we've done is we've sort of looked at all these cross sections. When z equals 0, what did it look like when z equals 0? A point. When z equaled 1, we had a circle there of radius 1. When z equaled 2, we had a circle of radius square root of 2. But listen, I mean, here's the contour lines that we just drew, but here they are living on the function. That's not what we do. We draw these contour lines in the xy plane like I did. So it's like you put your eyes up here and you look down and you see that picture. You see all these circles. But these little labels help. I mean, they help give you some height. I mean, these c values are z values, or I'd like to call that height above the xy plane. But what's subtle, what you can't tell too well on this is that when these things are further apart, when they're closer together, I think it means it's steeper.
Yeah.
Oh, yeah.
That's why I was
Equal potential.
When they're further apart, it's
It has to be, yeah.
it's less steep. But what you can't tell too well is that these are getting steeper and steeper and steeper, like a paraboloid probably would. Okay, it gets steeper as you go up this side, and these contour lines are kind of getting closer and closer together, which means, you know, from here to here we went up a height of 1. But that's a pretty good walking distance to go up a height of 1. From here to here, we went up a height of 1 in a lot less distance. We went up a height of 1 in a lot less distance. I would call that steeper.
Higher slope.
And then we went up another height of 1, and that's supposed to be less distance, and that's supposed to be even less distance. There should be less for each one I go here. It's getting steeper as you go. These little contour lines are closer and closer together, actually, on this example.
So we have to be super accurate when we draw a contour line.
Well, we should always try it for accuracy. Yeah. You know, here's some contour lines. Have you ever, I don't know if you've done any, you might have, well, you know, I don't know if you're in the military or if you've done some hiking or camping or
We've
mountain
seen them,
climbing.
Marine Corps. We've seen them in physics with equal potential.
Well, here you go. This is a contour map of some mountainous territory out west. This is 5,000 feet above elevation. This is 4,000 feet above elevation. Have you ever seen like a contour map? This is 3,000 feet above sea level maybe. There's 2,000 feet. I mean, that's a contour. Maybe you've seen contour map of
Yeah, I've experienced it with a compass.
trying to hike it. Yeah. So if you were here
Traverse it.
and you were trying to get here, I don't know. You might want to take the gradual approach. From here to here, you gain 1,000 feet of elevation. You know. So I don't know. That looks like a nice calm hike. You could do it however you want. Get up here and walk, right? That looks like a nice relaxing hike as opposed to,
I go straight a little bit.
right, some guy might say, dude, I'm gonna take a shortcut. He's gonna go over here. Try to go straight up the damn cliff, right? That's a cliff, right? He might beat you, but who knows? If you wanted to go down, I would recommend the cliff. I would. Good luck. So that's what these are. They're kind of like, you can think of these as elevations. They're Z values, and I like to think of Z values sometimes as elevations above the XY plane. Okay, good. So in 13.1, I just went over a couple of good topics. Sketch a domain, sketch some level curves. They're both techniques for two-dimensionalizing a three-dimensional surface. How would you know, by the way, looking at this one, you can sort of see these circular level curves. Maybe it kind of looks like maybe this is the top of a mountain, or maybe it's the bottom of a valley, right? It's either the bottom of a valley or the top of a mountain. How can you tell?
Because C equals 0 and Z equals 0.
Thank you. By the comparative C values. Right. These are higher C values. These are lower C values. So that would be the interior of a valley, I guess. Right. Doesn't take much. Some different, label this 10, 9, 8, 7, 6, 5 on down. Now this is the top of a mountain, right? This is the peak of a mountain now, and maybe it's an upside down paraboloid. We did just have that. Yeah. So it's subtle. The level curves might look the same, but the labeling helps decide whether it's a min or a max, or the top of a mountain, or the down in the bottom of a valley. Okay. So by the way, we're talking about functions of several variables, and for the most part, we're going to talk about, I said f of x, y, is z. I mean, we're talking about a function of two variables, which equals a third variable. This is our 3D world. Surfaces. These are surfaces that live in 3D. They're not curves. We're kind of done with that curves in chapter 12 there. These are back to surfaces. But all the stuff we learn in this chapter applies to multi-dimensions. I mean, so there's the occasional time we look at this. This is a function of three variables. We call it a function of three variables, but it equals a fourth variable we call w. And all of a sudden I'm in 4 dimensions. And I cannot draw pictures of him. I cannot draw pictures of him. I'm sorry. But I can draw maybe pictures of his domain. See, if this is a 4-dimensional thing, his domain would be a 3-dimensional thing. Right? Look, the domain is the ordered, I was going to say ordered pairs. You don't say ordered. They're ordered triplets. X, Y, and Z would be the input to this function. And it equals some fourth variable, but I could draw pictures of the domain because the domain is 3D. And if I drew level curves, they wouldn't be level curves, they'd be level surfaces. They'd be level surfaces. I mean, oh, look at this function. W equals the square root of 16 minus x squared minus y squared minus z squared. I mean, I know what, well, it's a four-dimensional thing. I can't draw it, but I kind of know what it is. Do you know what it is?
Is it kind of a
wormhole.
sphere? Kind
It is a sphere.
Oh.
Well, wait a minute. It's not a sphere.
That's a
It's the
sphere.
four-dimensional analogy to a sphere. Again, if you squared both sides,
The top half of that one.
you'd get your w squared
16 minus
Hemisphere.
would equal 16 minus x, right? Then move everybody over. You get w squared plus x squared plus y squared plus z squared equals 16. Did you follow that? That was two steps. I squared both sides and moved everybody over.
Whoa.
Two steps. Sorry. I squared both sides and moved everybody over, and I got a four-dimensional sphere of radius 4. I mean, but I can't draw a four-dimensional sphere. What if W was a 0, though? What if W was 0? I could draw the three-dimensional level surface.
The sphere instead of a sphere.
What would it be if W was 0?
It would be a sphere with radius 4.
It would be a sphere of radius 4. You're right. A sphere of radius 4.
Oh, man.
What would it be if W equaled 1?
That would be a sphere of radius
Square root of
square root of 15. Yeah.
Right? It'd be a sphere inside this sphere. Right, of a little bit smaller radius. But there's no way I can draw the four-dimensional thing. I can draw these three-dimensional level surfaces.
It's hard. You can't picture it.
You know what I could do?
That's right.
Yeah, you can't picture it. There's no picture for four dimensions, is there? There's this. Here, I know what there is. There's this. Everywhere out here at a radius of 4, I could put little numbers. 16, 16, 16, 16, 16. I mean, when you... Maybe this ain't making any sense to you. At these locations in space, the W value is... What's the W value at these locations?
It should be.
Yeah, you're kind of right. Hang on a second. That ain't what I wanted to do. That's not what I really wanted to do. What I was thinking of doing is going back. Now I'm abandoning level surfaces. I don't want to sketch level surfaces. Let's go back to this four-dimensional thing. How do I mean, I don't know. You know what I could do is at every point in space, I could try to find a W value. Let's do it. At 0, 0, 0, what would be the W value at 0, 0, 0?
That would be
64.
W would be a 4?
Yeah.
W would be a 4. So at that point, I should come out 4. No, there's no out. I don't left or right or up. No. Left or right is Y. Out and back is X. Up and down is Z. I mean, there is no damn dimension for W, right? No physical dimension. I mean, what I could do is color it some certain color. Or I was thinking of putting the number 4 right here, is what I was thinking. Did you guys say it was a 4?
Yeah.
Okay, put a 4 right there. What about over here at 0, 1, 0? Plug that point in there. Where do you get it? 0, 1, 0.
Square root of 15.
Okay, so I think I was going to put a square root of 15 right there. You know what? I think there's a lot of places. I could put square root of 15s at a lot of places around here. You guys agree? This is me. I come out here, it might be a square root of 12 out here. Maybe out here at this point in space there's some 1s. Maybe there's W has a value of 1 someplace. What am I doing? I'm representing the fourth dimension with just a list of numbers, I guess. I mean, and like I said, I could color those numbers. When they're small, they could be kind of bluish. They could go through the spectrum, I guess. They could get red in here.
Oh,
whatever. All right, let's move on. You know, so what comes next is section 13.2, and it's full of these interesting, crazy pictures. They discuss the continuities of these things. There's some crazy limits you can do with these functions. I'm skipping that stuff. And the reason they do a bunch of stuff with crazy limits, and they do some weird limits that don't exist, and it gets kind of crazy, but they do a bunch of limit work because they're heading into 13.3, and what do you think we're going to do in 13.3?
Take derivatives.
Yeah, we're going to take derivatives. And of course, the first way they define a derivative is with a limit. Again, I'm going to sort of skip over that. What I want to do now is show you how to do what's called partial derivatives. Here, I'm making up a function here. There's a function. I would like to take the derivative of this. And what happens now, we have z as a function of x's and y's. We have a function of two variables. When I say take the derivative now, there's sort of two derivatives you can do. You can take the derivative of this function with respect to x, or you can take the derivative of this function with respect to y. That was not ever really true before. This is with a function of more than one variable, with a function of two variables, we can take these two first derivatives. The notation would be this kind of curly looking d, because it's the partial derivative of f with respect to x. And I'm using a little curly d on purpose to indicate partial derivative. These are called partial derivatives. And this is new to you, although I think in your physics class you might have done a partial derivative or two. I'm calling it df dx. I could also, call it dz dx. I'm going to show you another notation. F with a little subscript x is the same thing, and that's sort of my preferred notation. It's a little easier to write. All this means we're going to take this derivative with respect to x. What that means is we're going to treat x like the variable, and any other variables we see we're going to treat like a constant. In this case, who's the other variable we're going to run into?
The y.
The y. So what we're doing when we take a partial derivative with respect to x is we treat x like the variable and treat y like a constant. It's a new thing. It's not that hard to do, but it does take some getting used to. You look staring at those variables and treating them like constants takes a little practice. So here I go. I want to take this derivative with respect to x. I should treat the y's like a constant, which means that y cubed is a constant. I think
12y cubed.
12xy cubed, or however, yeah, you guys were right. 12xy cubed. That's the derivative with respect to x. Minus
2y e to 2xy.
All right, hang on. The derivative of the e function is himself. The chain rule says you got to do this derivative with respect to x. 2y. Right, 2y. And you could write it out front, would be smart. Great. And now I'm taking the derivative of this with respect to x. 0. Yeah, I'll just put 0. Good. Good. Good, good, good. Let's do the other one. Do a partial derivative of f with respect to y. Or f with a little subscript y. But here we go. Now, and what happens is, again, you usually do these things back to back. And anyway, so your brain's got to switch gears quick. Now, y is the variable now, and x is treated like a constant.
18x squared y squared.
18x squared y squared.
Minus That'll be
e to
2x.
the 2xy.
And then that'll be 12. Plus 12.
And the derivative of the little 2xy with respect to y
2x.
is a 2x. 2x. And then the derivative of this guy with respect to y?
12.
12. Plus 12. Wow. So that's new. And we'll learn the meaning of these things. I mean, but I guess at the moment, I can spit it out today before we leave, I suppose. I mean, what is a derivative usually? A derivative is
So,
slope. Thank you. It's some kind of rate of change or slope. This is sort of a slope. It is. Yeah, hang on a second. You know, so if we got a function, f of x, y, what we just learned is that if I say take the derivative, I need to be more specific. You take the derivative with respect to x, or you take the derivative with respect to y. They're called partial derivatives. And so I can either take this derivative with respect to x, or I can take this derivative with respect to y. Right. There's sort of two first derivatives. What if you wanted to do a second
It's
derivative?
going to go to 4.
Yeah,
4 functions.
you're right. I can either do, because now I can go to him and I can take his derivative with respect to x again, which would be fxx, or I can take his derivative with respect to x the first time and then with respect to y the second time. And I like this little subscript notation for partial derivatives. I like it. It's convenient. It means this, though. Yeah, so with respect to y, hold on, I can take this derivative of him with respect to x, which would be fyx, or I can take that derivative with respect to y again, which would be fyy. In the middle here, you have these mixed partials here. They call these the mixed partial derivatives, second derivatives. And I just want to say that they're often equal. What does that mean?
They're often equal.
Yeah. So they're always equal, somebody says? No, I guess I didn't say that. They're often equal. They're not equal kind of maybe at weird places, and that's maybe where some of this limit discussion gets, but they're kind of not equal at discontinuities or very sharp points or strange places is when you have issues with these. If you kind of got nice continuous functions, these are often equal. I think this is a nice continuous function. I bet if we did the second derivatives on these guys, I bet we would find that these two would be equal if we did it to this one. But you can't walk away saying, oh, they're always equal. I guess not. But, and I don't really care about when they
So you
are.
can just keep taking the derivatives of either constant.
So,
That's pretty much what you're saying.
if
Well, and we don't need third derivatives too often, but I'm just pointing out that there's 4 possible second derivatives, right? Yes.
So if the definition of a derivative is a tangent line to the slope, what would the definition of one of these partial derivatives be?
Well, okay.
We have 2 tangent lines.
Well, here, I'm going to try to do this. Here's a picture. What is this a picture of?
Fish.
It is a surface, z equals f of xy. It's some surface living up above the xy plane. Maybe it's infinite. But if I want to take the partial derivative with respect to x, what I do is I hold y constant. So maybe we do this at a point. But I go over here to the y-axis and I hold y constant, which means maybe I take a cross section of it there where y equals 3 or something like that, and then the surface sort of becomes a curve. I mean, when I cut the surface at a constant y equals 3, then the surface sort of becomes a curve, and then when I find the slope in this direction, it is sort of the slope of the tangent line. in the direction of the x-axis. It's hard to see, but I cut it there. I could also cut it at some x. If I cut it at some x, that means hold x constant. Let y be the variable, and then I could calculate the slope in the y direction. Now the book has beautiful pictures, but this ain't a bad one. I like to walk around this room and describe this to you in this room, and so what I want to say, I'll say it, is that this partial derivative with respect to x, I'm going to say it is the slope of the surface in the x direction. Because, and it makes sense because the reason it's the slope in the x direction is because you are holding y constant. So, I'm on some crazy surface. Hang on. For y, I want to just say the same thing. Slope, it's the slope of the surface in the y direction. I almost feel like I should say that even a little better. I said the x direction. Here's what I mean by that. Okay, let's look at this. We're on some surface. There's a surface in this room. There's an undulating, beautiful surface. You can think of it as a putting green. I like to think of it as a putting green at a golf course. Anyway, I'm standing at some place on that surface, and if I take the partial derivative with respect to x, it is the slope of the surface in the x direction. What that means is, it's the slope in this direction, which is parallel to the x-axis. That's the x direction. It's the positive x direction, by the way. You held y constant. So it's like you slashed it, you cut it right here at this y value being constant, and you're looking at the slope in this direction. I'm going to add to this and say, well, hang on. And so then if I want the slope in the y direction, what do? I look that way. I turn my face that way, I look that way and see what that slope is. You know, they're not necessarily the same slope. I mean, this could be falling in front of me, and then I turn this way, and there's a cliff rising, here. I mean, so what we're learning is that there's not just one slope at a point. At a certain point on a surface, you can have that slope and you can have that slope, and they might be different. And I'm getting 3 days ahead of myself, but the truth is, I can find the slope in any direction.
Oh,
I mean, we start with these two slopes, the slope in the x direction and the slope in the y direction. Or really, the slope in any other direction is just made up of some formula involving those two. It's some little bit of this one and a little bit of this one, if I'm looking in this direction.
Keep it y constant.
Let me say this a little better. When I say in the x direction, I want to say, what does that mean? That means
Towards you.
parallel to the positive x-axis. And in the y direction, the direction is parallel to the positive y-axis. I mean, I don't want to complicate things. I'm actually trying to clarify things. I don't want you to say this. You're standing at this point and the slope in the x direction is, oh, I got to look over there. It's the slope in the x direction. I got to look at the x-axis. See, that's wrong. You don't want to look at the x-axis. The slope in the x direction is in a direction parallel to the x-axis, right? In the x direction. And it's positive. You know, the slope in that direction might, maybe I find that the slope is 6. You know what happens if I turn around and look behind me? The slope is -6. Wow, that's a whole new concept. That didn't happen in 2D. You know, in 2D, when we drew a slope, the slope was 2. We didn't say it was -2 or +2. It was. But if I'm standing at a point and I say the slope in that direction is 12, if I turn around and look behind me, the slope's -12. The surface is rising 12 in front of me. That means if I took one step in that direction, it would go up 12, kind of, right? It's got this, of course, it's all instantaneous. As soon as I do take one step in that direction, the slope might have changed, right? I mean, it's all instantaneous. Yeah, that's good stuff, you guys. That is good stuff. I tell you what, I might quit. It's early, but I think I'm going to quit.